And again, if you're getting so used to this is monotonous, that's a good sign. Because once again, let's do a subring test. So let R be a ring. And what's called the center of R is defined as follows. Again, we're not that we're reviewing right now. Won't worry about ideals. But we're just gonna again prove stuff with rings. Again, this is what's called the center of the ring. It's xy equal yx for all y in R. And so, in other words, what this is saying, and let me put this in words, i.e., the center of a ring is the set of all elements that commute with every element in the ring. So again, let's say it's a case, it's not a commutative ring. So what this is saying here, these are the elements in the ring that will commute with every other element in the ring. In other words, if you take, like, let's say this X, if you take it X times Y, it'll be Y times X for all the other elements. So that often if a ring is not a commutative ring, there will be some elements in the ring that'll commute with every others. And so the question is this a subring? And again, let's do the proof as usual. And let me use A and B this time so I don't confuse. So let A and B be in the ring. Excuse me, I take it back. In the set we're interested in the center. Sorry about that. That's going to be, we'll pick two elements in this set right here. Sorry, in the what we call the center of the ring. And then let Y be any typical element in the ring. So we're taking two elements in this set, but Y is a typical element in R. So supposedly then, when these two are in the center, they're going to commute with every element in R. So once again, let's go through our usual test. So let's start with, say, A minus B. So let's say consider, so the question we're asking is A minus B going to be in the center? Because that's what our subring test always is. We're taking the difference and seeing that if that's in the center. So if we try to commute it, let's say if we take A minus B, if it truly is in the center, then this should be equal to Y times A minus B. So let's go through the steps here. We have AY minus BY. And now because A and B commute with every element in the ring, then we can use that property to do this next step. YA YB. And then, of course, we can factor this out. YA be like this. And so what we did, see, we took A minus B and multiplied it on the left and found that that's equal to Y A minus B on the right. So that means that A minus B commutes with every element in the set. So that means it's in the center. And then do this. The next one, again, is A times B in the center. And so again, let's start. So the question is, we take A times B times Y. Is that ultimately going to be equal to Y times AB? So again, let me just do it this way. So if we take A, and once again, because it's B commutes with every element, we can rewrite this as AYB. And because A commutes with every element, we can call this YAB. And so we end up with Y times AB. So once again, we started out and said that we wanted to find out if we took AB times Y, if that was equal to YAB, and that's true. And so AB is in the center. So that is a subring. Once again, using kind of the same method we used before. Any questions on that? Questions at all? Show that A plus B, A minus B is equal to A squared minus B squared for all A and B in the ring. If and only if R is a commutative ring. And these are some things we just kind of take for granted. It's actually a pretty simple problem, but again, we sort of take these for granted. Now, so if we use the distributive laws, we can say stuff like, if it's a ring, we can say like A plus B, A minus B. If we use like the distributive laws, we could say, distribute this, we can say this is going to be A plus B times A. And then you could bring the minus out front. We'd be allowed that to be A plus B times B. And then we could say, distribute the A's, that'd be A squared plus BA. And we could distribute the B, AB minus B squared. But now here, of course, if it's just a ring, we can't go any farther. Stop here. If just a ring. But if it's a commutative ring, we can say a squared, and then we could commute these to AB minus AB minus B squared. And then we can say that this is going to be A squared minus B squared. So again, something we just sort of take for granted, but if we have a structure in math, which is a ring, we could multiply through and get down to this point here. But if it's not a commutative ring, we have to just leave it like that. On the other hand, if it's a commutative ring, then we could go ahead and multiply that. We could switch these, and then we end up with that. And so again, it's just little things you have to kind of be aware of. And some of these are pretty straightforward. Oh, and also again, this really won't be on the exam, but something we should like cover when we're talking about especially when we're talking about mod stuff. And you've done this in some of your classes before. So let's say if you have a problem, and this I'll call this one from book got number 2. So solve 3x equal 2 in Z7 and in Z23. So in Z7. So really, you can kind of just look, if you want to be sure, you can just try all the values, see what would actually work. So for like Z7, if you wanted to be sure, you could just try all the values of x0, 1, 2, 3, 4, 5, 6. And if you put 0 in here, 3x, of course, is going to be 0. 3 times 1 is going to be 3. 3 times 2 is going to be 6. Now, 3 times 3 will be 9. But that's going to be what, 2, isn't it? Mod 7. Because 3 times 3 is 9, but that's going to be 2 mod 7. So that's going to work. That'll be one answer. 3 times 4 is 12, which is going to be 5 mod 7. 3 times 5 is going to be 15, which is 1 mod 7. And 3 times 6 is 18. So that's going to be what, 4 mod 7. So the only value that will give us 2 will be 3 here, huh? So excuse me, for x equal 3, yeah, x equal 3 gives us 2 right here. Any question on this? Now on Z23, so this one's kind of interesting. If we do Z23, now one thing all the way up, you figure if you put, let's see, if you put values into here, when will we start getting above 23? At maybe like 8, huh? So everything up through 8, we're not going to end up having. So in other words, if we put 1, 2, 3. It'll just give us values greater than 2. And then now once we get a like 8 or above, like if we put 8 in, that's going to give us 24, which is 1. And 9 will give us 27, which is 4. And then 10 will give us, let's see, am I doing that right? Did I do that last one right? Not 3 times 9, 27. Yeah, it's 4. And then 10 will give us 7. It'll keep increasing. You can kind of see the pattern. It'll keep increasing by 3 every time until we get back up to 23. You could actually multiply them out, each one, just to be sure. Or you can kind of like see the pattern, because the remainder, once you get like to 8 and above, the remainder will be 3 added to the previous one. 13, 16, 19. And then the next one will be 22. And now the next one will be 16. 3 times 16 is going to be 48. And that's going to end up being 46. That's going to end up being 2, huh? Because if we take 48 mod 23, the answer is going to be 2, because, again, if we take, like, say, 48 divided by 2 times 23, that'll be 46. So that'll give us that'll be one solution. So that gives us 2. Then if we go 17, again, we'll probably just be increasing again by 3 each time, if I'm thinking this right. So in other words, the next one will be 40. This will be 30. Excuse me. 17. Yeah, there'll be 17 times 3, which is 51. And then divide that by 46. And we're going to end up getting 5. So once again, it looks like it's increasing by 3 each time. And that would be 20. So the only solution is 16, it looks like. Like I said, so basically what I was doing here is I'm saying that until this gets past 23, the values, if you put like 1 in here, you're going to get 3, you get 2 is 3, up till the point where this ends up being 23, the values that you get will all be 3 times that number. In other words, they'll all be a number, they'll all be big numbers less than 23. Then once you get to x equal 8, then 3 times 8 is 24. Then the mods start kicking in. So this will be 1, 4, 7. Like I said, you could actually do all the steps if you weren't sure. But it's just sort of a quick way to do this. So it looks like the only solution then for this, so only solution to 3x equal 2 in Z23 is x equals 16. Kind of an odd solution. And let me try a couple of others here. Let's try this one here. Yeah, that might be, this one might be too long. Let me try this one. Actually, this is number 3 anyway. Find solutions. To x squared 2x plus 2 equal 2 in the 6. And so again, if probably the easiest thing, since these 6 is pretty small, just try them all. And then just see what you actually get when you put them in. So if we put 0 in, we're going to get 2. And if we put 1 in, we're going to end up getting 5. If we put 2 in, we're going to end up getting, that would be 4 plus 4 plus 2 is 10, but then mod 6 is going to be 4. Remember, we want is 0. And then this one, that's 9 plus 6 plus 2 is going to be 17, I think. Again, if we do that mod 6, it's going to be 5. And then the next one is going to be 4 squared, 16, 24, looks like 26. Mod 6 is going to be 2. And then 5 squared, 25 plus 10, 35, 37. Mod 6 actually looks like no solutions, huh? Because we didn't get 0 on any of those. Any questions on that? Okay, let me just do one more like this again. Because you might do this in some of your other classes. That you might possibly, yeah, well, actually, let me do this simple one here. This is pretty straightforward. And again, sometimes you can even, we can possibly even factor these. So let's take a look at this. Find solutions. And so let's take a look at this. Zero, 1, 2, 3, 4, 7, 8, 9. And so again, we put these values in 0, of course, that's going to be 6. If we put 1 in, that's going to be 6 looks like 12, if I'm doing that correctly. And that's going to be mod 10, that's going to be 2. And if the next one, it's going to be 4 plus 10 plus 6 is going to be 20. So that one looks like that's going to work, huh? That'll be 0. Then the next one is going to be 9 plus 15 plus 6, which is going to be 30. And it looks like that's going to work. And this one's going to be 16 plus 20 plus 6. And that's going to end up being 42. That's going to be 2. That won't work. And then it's going to be 25 plus 25 is 50. Going to be 56. Mod 10 is going to be 6. This will be 36 plus 30 plus 6, like that, 72. Mod 10. And that's going to be equal to 2 mod 10. And if we did 49 plus 35 plus 6. So that's going to be, looks like that's going to be, end up with a 0. That'll be 41, looks like 90. And that's that'll work. And then the next one, 64 plus 40 plus 6. And that's also going to end up with a 0 on the end, huh? So, because that's going to be 70, was that 110? That's going to be, that'll work. And then 81 plus 45 plus 6. Doesn't look like that's going to end with a 0. So it'll be like 51, and like looks like 131, something like. Am I doing that right? 9. Sorry, 132, huh? And that's going to be 2. That many kids, that's not going to work. So actually, the solutions are. Now, the reason I just wanted to do this, let's see if we could actually factor it and do it the same way. So the solutions are x equal 8. But let's try by factoring. Let's see if we can try by factoring. See if that'll make it a little bit simpler. If we factor it, x plus 2, x plus 3 is 0. And let's see if we do the same thing, if we can simplify. Let's see, x is 0, 1, 2, 3, 4. Over here, 5, 6, 7, 8, 9. So again, if we factor, so this is going to be 2 times 3, which is going to be mod 10. That'll be that's still going to be 6 no matter what. And then over here, if we put a 1 in here, this is going to be 3 times 4. And then mod 12, that's going to be 2. 12 over 2. Now, if we put 2 in here, this will be 4. And this will be 5, which is going to be 20, which again, mod 10 is going to be 0, which we got previously. And if we put 5 times 6 is going to be 30. That's going to be 0. If we put 4, that's going to be 6 times 7, which is 42. Mod 10 is 2. If we put 5 in, that's going to be 7 times 8, which is 56. Again, mod 6 is going to be 6. 8 times 9 is going to be 72, which again is going to be 2. And 7. Now, one thing to notice here, when we put 7 in, we'll get 9 times, this is going to be 10, huh? But mod, so actually, let me put this down though, but mod 10, that's going to be 0. So we could actually right here put a 0 mod 10, right? So we would know that that's going to be a 0 right there. Sorry, my lines are messed up here. Let's see, I messed something up, didn't I? No, that's right. Then find the same thing with the next one. Notice that this one is a 10, and this one's going to be 11. So we can apply the mod right here. So it'll be 0 times 1, and that's going to be 0. The next one here, this is 11 times 12. Again, mod 10. That's going to be 1 times 2, which is going to be 2. I guess the point is, again, once you get, so if we factor, we could simplify things quite a bit, because anytime we put anything over here becomes greater than 10, we can apply the mod and reduce it right away. It kind of simplifies our arithmetic. But so the point is, I guess you can do these problems either way. If you're able to factor them, you can go ahead and factor them and do them this way. More or less the official definitions. Which doesn't have to be exactly like these, but this would be a good, say, starting point. And cardinality, I don't know if we really talked about that a whole lot. That's really just the number of elements in the set. And again, you have 1-to-1 and on-to from the previous course. So you had both of these. Again, like I said here, there's several ways to define this. And you can use this or maybe your own. Disjoint sets, we've kind of sort of talked a little bit about this indirectly. These are just simply two sets that don't have any elements in common. You know, it could be, sometimes the sets could be thought of as like in picture form, where they're like disconnected. Or you could have like, you know, the actual elements, let's say 1, 2, 5, and 8. You know, and like 10. And it doesn't have to be starting at those higher ones. It could be like maybe they could be like 3, 4, 15, you know, just simply two sets where there's no common elements. And when we're talking about partition, remember the partition, they were all disjoint sets. Remember, they didn't have any members in common. A partition is decomposition into non-empty subsets such that every element is in exactly one of those subsets. And remember, the equivalence relation partitions the set. And again, the cells of a partition, these are the subsets of the partition. Again, remember, it breaks up a set into those partitions. Equivalence relation is a relation that is reflexive, symmetric, and transitive. Equivalence relation will partition a set. Again, the equivalence classes, those were each of those sets created by the equivalence relation. Remember, we did a lot of problems with equivalence relations where we broke the original set into sets, into smaller sets, and those were called the equivalence classes. So really, like all of these kind of things here kind of all relate. Disjoint set, partition, cells, they kind of all related to each other. Any question on that first page? Anything that's not clear there? And go to the next page. A binary operation on a set operation on any two elements of set that result is an element in the set. An operation is closed if for all elements in the set A and B, A star B is in the set. Now, I suppose like here, I'm not sure like on the binary operation, if I needed to put that the result was in the set, you can leave that off if you want, or you can put it in, because generally closure is usually a different thing. Again, it's closed if the operation results in something in the set. Again, I'm sure by now you know what commutative is. An operation is commutative if A times B is equal B times A for all elements in the set. And it's associative if this is true. And then for sure, be sure to carefully know the definition of a group. And actually, you know what? I've made a mistake here. A set with an operation, say, a star, and I should really, I think what I really mean here, if you could please fix this for the group, you could say this is a group. Yeah, that's a typo there. That should say a set with an operation, say star is a group if and maybe this isn't quite it, if it is closed. I should maybe even say closed under star. Yeah, I should fix that. Yeah, so that's be a little bit better. This is certainly a typo here. A set with operation, say star, is a group if it is closed under the operation, has an identity, each element has an inverse, and it's associative. And like I say, I always, if you try to remember this, it's always CIA. Has to be closed, has to be identity, has to have an inverse, it has to be associative. And a abelian group is a group such all the elements in the group commute. And a subgroup is a subset of a group that is itself a group. A subgroup test is a subset H of a group is a subgroup if for all A and B in H, A star, and this could be an addition if addition is your operation, B star, excuse me, B inverse is in H. And a cyclic subgroup, this is a subgroup of a group is generated by the element of the group. You know, usually we represented it, as I mentioned earlier today, you know, maybe like something like this. You don't need that symbol, but that we're doing. And that's what below here is going to be that generator, like in this case, A. This is the element of the group that generates the subgroup. Any question on that page? Yes, sir.
What does it mean by generates a subgroup? Like there's a, what is that element?
Yeah, so what this is, let's say if your operation was addition, so let's say, for example, consider consider the integers. In fact, when we think even one of the ones we use today could have been generated by this. So like, for example, if we have like 5, oh, sorry. So one of the ones we did today was like say 5. Now notice 5, if you take 5 plus, if you take like all the multiples, let me say it this way, this is probably a good way to say this. If we take 5 n such that n is in the integers. So this would be a way, so you can think of adding 5 to itself over and over and over again, and also subtracting 5 from itself over and over again. And you'll end up getting, if you start in the negatives, you'll end up getting like, say, -15, -10, -5, 0, 5, 10, 15. So by adding 5 together to itself over and over again, if addition is the operation, then it'll end up generating all of these members here. Now, in this case, then this end up being, when you do this, this end up being the subgroup 5Z. So in this case, we can say that 5 will actually generate this group, because if you add 5 together with itself over and over and subtract it over and over, all the possible ways, it's going to give you that whole subgroup. So therefore, we call 5 the generator. Yeah, good question. Any other questions on that? That makes sense. And if it's multiplication, then you would maybe multiply the thing over and over again with itself to generate the subgroup. Any questions? And yeah, greatest common divisor. And you use that a lot when you're doing the stuff with the subgroups. Remember, you're doing a lot of stuff with figuring out what are the possible orders of subgroup. And again, if you factor 2 numbers as much as possible, the largest factor in common is called the greatest common divisor. We kind of work with that a lot. And then if the greatest common divisor between 2 numbers is 1, the 2 numbers are called relatively prime. So that would maybe be like, for example, 8 is going to be 2 times 2 times 2, and 9 is 3 times 3. So there's, and of course, you can always think of there being a 1 there. So the greatest common, so these 2 are relatively prime. Because the largest factor that they have in common is going to be 1. And this one, just know how to do modular arithmetic. The intersection, of course, you know what the intersection of 2 are. And a permutation on a set, there's a function on a set that's 1-to-1 onto. I don't know if I actually gave you, I don't think I gave you any permutation practice problem, did I, for the exam?
Well, I think there was one that we did
On the practice.
last weekend, not on these ones.
Okay.
Like
Okay, yeah.
Yeah,
okay, yeah. So be able to do sort of those basic ones, yeah. So be able to do those basic ones. In fact, I'll probably, yeah, that, in fact, you're right, the homework would be a good example. And this one, you can maybe leave I just called this at SN group. You can maybe, I probably won't ask you anything specific. You just be able to use, you'll be given that chart for the S3 group. And so just be able to work with that chart. And like I say, you'll be able to use that. And yeah, I guess the same with orbits and cycles. That was on that last homework too, I think, huh? Yeah, so be able to calculate those and know how to do the left cosets and the right cosets. Any question on that? Yes, ma'am. Yes, just be able to, right, just be able to calculate them. Just be able to do the whatever your subset is, yeah, just be able to calculate them. That's right. Be able to do that one for the left, and then this one for the right. Any other question on that page? And yeah, so again, no Lagrange. And actually, there's some practice problems they gave you for those. So suppose that G is a group and H is a subgroup, and the order of H must divide G. And every group of prime order, oh yes, cyclic. And so again, the idea is that, let's say, and let me take a simple example. If you have like, say, Z5, you can generate, so if you take 1, and if you add it to itself, you get 2, 3, 4, and then when you get to 5, it'll be 0. So in other words, if a group is a prime order, then there's going to be an element that can generate the whole group. And actually, I think in the case, yeah, actually, I think in the case of like something like this, any of the elements will generate the whole group. If you have a prime, if it's a prime order, at least when you're working with these mod, like say a Zn, if the n is prime, I think any element, like for example, if you tried to do that with 3, you would get 3, and then 3 plus, oh no, maybe not. Maybe I'm messed up here. 3 plus 3, yeah, 3 plus 3 is 1, and then 3 plus 1 is 4. 3 plus 4 is 7, then mod 5, that's 2. And then and 3 plus 2 is 5, which is 0. Yeah, actually, I think, yeah, if you're dealing with a Zn where n is prime, then you can generate the whole group really with any element. Though I'm really asking you just to say there's a single element, but in most cases, it's going to be true that you can pick any element in the group and get the whole thing. And there's a definition of a ring. Again, it's a abelian group under the first operation, associative under the second. And also, yeah, one thing I mentioned before the head from that one book, we should also put in here that it's closed as well. So please put that in closed under star, under the second operation. And the multiplicative inverse, multiplicative identity is 1, and unit is any member that has an inverse. And we'll go over any of the other practice problems that you have for next time. So take a look at all the other practice. But again, I think this exam will be easier than the real analysis exam. Though, but again, there's going to be some sort of proofs you have, but it's I think it's going to be easier. So any questions on anything?